What's happening, folks? Geologist Philip Prince coming at you with a rare sighting on this channel. A picture of a person and a rock. Most of what I do is from the mountain range scale or the continent scale. It's rare to see something zoomed in like this, but this rock's an absolute standout. It's a giant boulder. It probably weighs about 40 million pounds, and it fell from a cliff about 1,000 feet away and slid into the place that it is today without completely falling apart. Kind of a unique set of circumstances for it to end up this way, and it is probably within the top 5 largest boulders anywhere in the Appalachian Mountains. Going to talk a little bit about how you might find things like this in the Appalachian forest, as well as how a feature like this might form in the first place. This one's in Transylvania County, North Carolina, Pisgah National Forest, the Appalachian Blue Ridge, Looking Glass Rock's pretty close by. You got Mount Pisgah and Asheville there for reference. There's a lot of steep topography in this view. There's a lot of rock cliffs and there's a lot of boulders in the landscape. But the one you saw just a glimpse of moments ago is an absolute standout here. Within this entire view, it is absolutely without question the largest boulder that you're going to find anywhere. And in terms of appreciating that it actually is a boulder that moved to get where it is now, that's kind of tough to do. If you look at it from the end, it looks like bedrock sticking up out of the ground. But if you step back far enough, you can see it. It actually does have ends on it. It's huge. If you put a person on it, it would look something like that. It's about 135 feet long end to end. It'd be 50 or 60 feet wide. It's about 18 meters wide. And as far as how far down into the ground it goes, it's hard to say, but it's probably at least 30 feet thick, just shy of 10 meters thick. If you take all these dimensions, multiply them together, you can get a volume of this boulder, and you multiply that volume by 168 pounds per cubic foot. That's how much a cubic foot of granite weighs, and this boulder is a granite-like rock. That's how you come up with that crazy weight estimate. So it's not just a number out of thin air. You actually can look at something like this and get a sense of how much it might actually weigh. Now, how do you find something like this? I didn't just happen upon this in the woods. I used remote sensing to find it, and that is LiDAR imagery. I work with LiDAR every day in Western North Carolina. Most of what I do with it is assessing landslide risk in the landscape. But when you're doing that and surveying large tracts of land, occasionally you see things like this really awesome giant boulder and the scar that it came from and this kind of rough area that it plowed up when it went down the hill. It did that a long time ago. The forest has grown back, but you can still see traces of that in the landscape. And when you find something like this, of course, you got to go out and look at it and see what it actually looks like. Luckily, this was in Pisgah National Forest, and there's actually trails very close to it that allow you to get to it pretty easily. You can see a huge amount of detail with that LiDAR imagery without even going there in person. Got kind of part A and B here. A is this little bit that fell over forward off of the boulder there. And you can actually see that with that LiDAR imagery if you tilt it so you're looking along the ground surface. So it's a really cool technology to play with and get paid to play with. And when you can pair it up with actually going out in the field, it makes for a really exciting combination. The detail that you can get from LiDAR is absolutely incredible today. You can see that crack that I was stepping across at the beginning of the video. It's a little dark line down there at the end of the red arrow. Part A and part B there, again, A being that bit that fell off. You can, of course, see that in the field very nicely. And you can have a sense of what a boulder like this is going to look like before you even get there in person. So when you spend days and days and days looking at a mountain landscape with technology like this, you get a pretty good idea of what you can expect in the landscape in terms of boulders. And that's how you can say that the one you're looking at here is absolutely unique for the region. Now, how did it end up breaking loose from a cliff like that, sliding, not falling apart, and ending up again about 1,000 feet or 300 meters away from where it started? Got to think a little bit about the geology here, which is somewhat unique. Everybody likes it when you put an adverb on unique on this channel. So I just did it again. Somewhat unique for the area, but not completely unique. You want to think about what's inside the side of this mountain and what's inside that cliff that the boulder came off of. Got to use a sketch for that. Going to hop out to Microsoft Paint, show you what it looks like. Hang on just a minute. Okay, here we are in Paint. Going to try to sketch out how a cliff capable of producing a really giant boulder might develop in the landscape. We're going to use typical kind of block diagram style here. So we're going to try to set up this cutaway view. And you may already be able to tell where the cliff is going to go here. We'll have some vegetation up on top of the cliff there, and then we'll have trees again down here at the bottom. But the cliff itself is going to be that bare rocks. We'll fill in our forest there. It's going to be the cliff at the surface. Now we're going to need a little bit of subsurface geology there. So the rock that's forming the cliff is going to go down under the ground like that. Going to keep that nice light gray color. And the rest of the rock here is going to be something very different. We're going to color that with a different color. Now, first things first, this rock's going to have some kind of internal structure here. So we'll say that this is going to have a bit of mineral alignment in it. It's not uncommon for rocks that are granite-like in the Appalachians, you might call them granite gneisses, to have mineral alignment like this. Geologists call it a foliation, but fundamentally it acts kind of like a layering in the rock. And what that layering is going to do is provide one set of slightly weaker surfaces in the rock that are going to help it fall apart. Now, step two, which is probably the most important on a feature like this, is what are called exfoliation joints. Rock like this formed very deep in the earth under a tremendous amount of pressure, and as it's been uplifted and exposed by erosion, that pressure is no longer present. So the rock is actually trying to expand outward. In quarries, this produces a phenomenon called rock bursts, which are actually kind of dangerous to work around. But in nature, you just think of it as the rock trying to expand outward due to that pressure release, and those exfoliation joints end up intersecting with the mineral alignments. And what we're going to represent on our cliff here is kind of this gap area in it, as if there's already been some kind of a failure here in the geologic past. Now, that gray area is going to have a really different internal structure from the purple out here, which might be a more mica-rich rock type like a schist or something. And ultimately, the difference in these two rock types is why there's a cliff there to begin with. Now, let's zoom in a little bit closer here and focus on this area where you've got this overhang that's developed because there's already been a large failure in the rock where those weak planes are intersecting with the steep exfoliation joints. Okay, so now that you've got another weak spot here, let's pretend that happens again, and we'll have this weak surface cause a failure that's going to clip out this whole big block here, all right? And it's going to have all those foliation layers within it. That's going to become important momentarily. So let's slide that thing off the cliff. It's going to break away and slide down here onto the flatter land. So to make that happen, we'll just turn that into another gap in the cliff here. Okay. So the developed roof feature there would probably be a pretty cool climbing challenge. But the big takeaway is that now there's a big old chunk of rock that came off of that cliff, and it's sitting down there on the forest floor. Now, the cool thing about this is, one, it didn't totally break apart because it was able to kind of transition nicely out there onto that flatter slope. And a cool detail that you can identify if you get up really close is the fact that that fine foliation layering in it is now pointing straight up and down. It started off being horizontal on the cliff, and that allows you to kind of record that journey that boulder has taken down there to the flatlands. But when you're dealing with rocks like this in the Appalachian Blue Ridge or Piedmont, the fundamental elements are the exfoliation joints and how those intersect with other weaknesses in the rock. And when those get together, the rock is already pre-broken and it allows big pieces to easily come loose. And if the slope has the right shape, they can transition cleanly down there onto that flat land and end up moving a pretty good distance from the cliff without totally falling apart. Let's hop back to it now. Okay, so that's the basic idea here. You have to have the right combination of joints or fractures in the rock. You need some other weak planes in the rock to intersect those joints and fractures, and you need the right topography for that big piece of rock that comes loose to slide down on without starting to tumble and completely breaking into pieces. So it's kind of a cool combination of circumstances that came together to allow this feature to form. And if you went nearby to good old Looking Glass Rock, you might expect to see something similar. The geology is pretty similar in that area, and with that much steep topography and the right combination of these weak planes in the rock, you might expect to see a lot of boulders. You do indeed see them, but the ones you're looking at here are actually only about half the size of the one we started out with. Could Looking Glass produce a boulder of that enormous size that you first saw? Yeah, that's entirely possible. You would just have to be here sort of at the right place and right time geologically. But suffice it to say, enough similarities are shared between Looking Glass and what we started with there that you could expect a generally similar behavior between these rock masses. In the Appalachians, rock type varies significantly within the different parts of the range as you see it today. So Looking Glass and the first boulder are in the eastern part of the Appalachian Blue Ridge near its boundary with what we call the Piedmont. Both of these areas have sort of a characteristic topography associated with them. They both have metamorphic and a bit of igneous rock, but there are some subtle distinctions that allow those to evolve differently and give you a different topography. The Valley and Ridge and Plateau have their own geologic structures and styles and thus their own topography. And the Blue Ridge Escarpment is one standout feature here because it puts rough Blue Ridge style topography actually out in the Piedmont. So when you're thinking about the Appalachians, when you see the mountains and the different parts of them look different, that's because the geology underneath them is different. And that geology ultimately is what's going to have the right variables to make really giant boulders. Biggest boulders are going to occur in the eastern Blue Ridge or maybe the western Piedmont along the Blue Ridge Escarpment, or actually out in the Appalachian Plateau where sedimentary layers haven't been folded or faulted. The western Blue Ridge, the Valley and Ridge, yes, you can find big boulders there, but they're not going to be as large as what you get in these two pretty widely separated zones of the Appalachians. So that image you just saw is like if you cut the mountain range open from somewhere in East Tennessee all the way down into upstate South Carolina. The line you're showing there, which would be sort of what you're looking at in terms of that cross section, goes from the Big South Fork in East Tennessee to something like maybe Spartanburg or Union County, South Carolina. So it goes all the way from the Appalachian Plateau down southeast into the Piedmont. And we're going to kind of take a tour along that line and look at some other really giant boulders that you can see with this LiDAR imagery that are comparable in size to that really big one we started out with. It's located there in the Blue Ridge and Pisgah National Forest. Next one to look at here is actually going to be out on the Blue Ridge Escarpment. Then we're going to go over to the Plateau, look at the Obi River, the Big South Fork, and all the way up to the Red River Gorge there. So this is kind of the tour de Boulder through the Southern Appalachians. So starting off here, there on the right, Big Old Rock. That's what I'm going to call this one. It actually has a local name. It's on private property. I'm not going to use that local name, but it's near Chimney Rock. That's about all we're going to do there, and it stands out very nicely on this LiDAR imagery. You can see it circled down there. It's actually about 150 feet long. It's a little bit bigger in terms of length than the first boulder in the video, but it has broken apart, and it has these three big cracks or fractures running through it. Now, in terms of its overall volume, is it bigger? There's really not a way to know that. It is very, very close to the first boulder in the video. So much so, in fact, that you could probably say that they're essentially the same size, which might be thought of as just kind of a cool coincidence, but maybe not. And that's an idea that we're gonna finish with at the end of the video. Now, what does this one look like from the ground? Well, you can walk up into this big crack that's splitting the boulder right up the middle, and it looks something like that. Absolutely huge exposures of rock. Again, really no way to tell from the ground that this isn't just bedrock sticking up out of the ground. Crazy caves and fissures developed in it. A really, really unique looking landscape. And again, one that is kind of deceptive from the ground. You got to have that LiDAR perspective to really figure out what's going on here. But in terms of its overall size, again, it's really not fundamentally different from the one we started out with. So now let's jump way to the northwest to the Appalachian Plateau. Take a look at a slope going down to the east fork of the Obi River. It's going to be out in this part of the Appalachians where there's flat lying sedimentary layers. This is what the landscape looks like with LiDAR imagery, and it's got plenty of big boulders in it. They just look like absolute pebbles here. They're really, really big. The ones at the end of the arrow there's two of them, be about 120 feet long in their longest dimensions, so something like 35 meters long, something like that. Comparable in size to the two that we've already seen. And you can see there's quite a few other boulders that are really, really big in this image. These are all made of sandstone, and they're breaking away from these big flat-lying sandstone layers that sort of cap the plateaus in this part of the Appalachians. Let's go up northeast to the Big South Fork of the Cumberland. I think this one's a really cool view. Got two huge boulders there. You can actually see the path they plowed down the slope as they came downhill. Broke away from the sandstone cliff up here and ended up having traveled down a really, really steep slope, and they didn't break all the bits. And that's testament to the mechanical strength of the sandstone that you get in this part of the Appalachians. Out there in the Blue Ridge and Piedmont, where there tends to be a lot of mica in the rocks, and those micas tend to line up to produce what we call a foliation, that produces planes of weakness in the rock that allows the rock to fall apart more easily. You don't get that in some of these big, thick sandstone layers. So they are really the absolute kings of boulder formation in the Appalachian Range. Let's go up towards the Red River Gorge in Kentucky. Really cool landscape here to look at with LiDAR as well. You can see those crazy sandstone layers capping the topography. And again, the landscape's just absolutely littered with boulders. These are a little bit smaller. Most of the ones you see here would be 30 or 40 feet across. So they'd be 10 or 12 meters across. But there are a few bigger ones, and they're absolutely everywhere in the landscape. It's hard to get a sense of it if you just look at Google Earth. You sort of need to be able to see that bare ground as you can with the LiDAR imagery here. So anywhere in the vicinity of the Red River Gorge, which is itself so dramatic because of this sandstone cap rock that kind of props up the walls of the gorge, you can expect the slopes to look like this. Cool detail from this image. He's got a boulder here. This one's about 40 feet across, about 12 meters across. You can actually see all the little scars in the slope where it rolled down the hill. So in this particular case, this wasn't a case of sliding. This is very much a case of tumbling, but this boulder was the right size and strong enough not to fall apart while it did that. And you find stuff like this with some regularity when you look at the slopes with LiDAR. Going up into one of the main, I don't even know what this creek's called. It's one of the main tributaries of the Red River Gorge. You'll see it on Google Maps here in just a minute. Uh, Landscape with Google Earth, hard to get a lot of detail out of it. You can see these sandstone cliff lines. If you throw LiDAR on it, it looks absolutely crazy. And you have these really dramatic cliff lines. A lot of them are quite geometric, and you can see all these boulders littering the slopes below there. This is where it is. The main Red River Gorge is actually right down here off of the bottom of the screen. And from Google Maps terrain here, you can get some sense of the grain of this landscape, although it's never going to be quite like what you get when you have that LiDAR imagery. So zooming in closer, again, you can see these cliffs here actually just in the Google Earth satellite imagery, but with LiDAR, they look absolutely crazy. And these are big boulders, 80 feet, 80 feet wide, most of them, like 25 meters or something like that. They look small because the overall scale of the landscape is quite big. But if you went and walked up to one of these, they would probably have soil and trees growing out of the top of them. So they're big enough to actually turn into almost part of the forest floor after they've fallen off and been in place for quite a while. Kind of a cool cliff line here. It has that kind of like cornered right angle shape. And momentarily, we're going to talk about what that represents. Really nice boulder that's come off down there. That's the same one down there at the bottom right. And these are about both of the ones at the ends of the arrows here, about 120 feet against like 35 meters, something like that. So almost the scale of the two first really big Blue Ridge and Piedmont boulders. Now, what makes this landscape look this way? You have these really dramatic gorges. It's kind of geometric cliff lines here and a bunch of really huge boulders that have fallen off of those. Again, gonna have to sketch this out and actually think about what's under the ground and how geology controls it. So we're gonna hop out to paint again, draw up a sketch here. Hang on just a minute. Okay, so paint round two, going to show you what the Appalachian Plateau landscape is going to look like. This is going to be pretty distinct from the Blue Ridge or steeper parts of the Piedmont because of the underlying bedrock geology. This is going to be a cap rock landscape where flat-lying layers of sandstone define everything. And I'm going to slowly but surely draft in this landscape so you can see why it looks like it does. Probably going to run a fair amount of this in fast forward just because there's a good bit of complex topography to show here. But when we come back together, I think you're going to see that this is really, really different from the first giant boulder or the looking glass example. So hang on just a minute. We'll get this finished up and be back with you. Okay, so here's the cutaway plateau landscape, and really the center of attention here is going to be these flat-lying sandstone layers that form the cap rock in this landscape. Sandstone's very hard. It's very difficult to erode in compared to the shale or potentially limestone underneath it. It's just a whole lot tougher. That's why it forms the cap rock through long-term erosion. And that cap rock is always going to have, in a situation like this, where the rivers have cut into the landscape, some kind of a pretty impressive cliff around the edges there. Now, in addition to the sandstone layers, which do have these horizontal partings between the individual sandstone beds, this whole landscape is going to be cut up by plenty of joints. Of course, we already talked about joints in the Blue Ridge example. These are a similar feature in that they're pre-existing weaknesses in the rock. A lot of times they reflect tectonic stress or stress on the rock layers while they were still very deeply buried. They can also be a result of stress relief as this deeply carved gorge here has kind of taken the support away from the sandstone and it's trying to expand outward into that free space there. One way or another, throughout the Appalachian Plateau, there's plenty of these, and they cut up the rock and they're very continuous throughout the landscape. So when a geologist looks at a place like this, the geologist is seeing these continuous joints. That's one set. They tend to be very steep, so they're almost vertical in most cases. And then there will be another set that cuts across those. And the entire landscape is basically cut up into these kind of bricks or blocks. And if you think about those Red River Gorge landscapes, they are incredibly geometric. A lot of places the cliff line actually is sort of rectangular or square. It has a lot of these 90-degree corners. That's a result of this natural joint development or fracturing in the rock. Now, when you have those joints intersecting with the sandstone layering along a steep cliff, that's a pretty good way to make that cliff fall apart, and we'll do that now. So let's say this joint is a failure surface. We're able to carve out a nice big chunk of sandstone there. We'll turn that into a gap in the cliff line. And downslope of that, you've now got maybe 3 really big boulders, assuming everything falls apart on those sandstone bedding planes, the sandstone layering planes. So that's the fundamental idea. And we can now draw the new cliff line in there. So it's going to have this kind of rectangular gap in it where the sandstone fell out and produced those giant boulders. We can go do that on the other side now. There's another example that's nice and ready to go there. Do the same thing, get rid of that one, make ourselves a new cliff line. Keep our sandstone layers kind of running through there like we need to. Fill it back in. And we got some more big boulders sitting down on the slope down here. And if you were the type of person that enjoys bouldering as recreation, this process that we're illustrating is probably your favorite geologic process, because that's creating all of these really amazing outdoor features that you're able to interact with. And you can imagine this happening throughout this entire landscape, and over time, all of these slopes are going to be littered with big sandstone boulders that have slowly but surely detached from the cliff lines and come tumbling down the slopes. Now, an interesting process that happens in this landscape with less frequency is sort of larger scale landslides, and they use the same geologic contrasts, but the ultimate result of them is a little bit different. So we'll clean up this first boulder pile here just for clarity, and I want to reshape my slope just a little bit to have it steeper at the base of the cliff line there. So in this particular case, you might imagine failure along this joint actually cutting down through the shale underneath it. Shale is a very soft, weak bedrock, and just due to the weight of the sandstone above it and the shape of the slope, maybe that shale just can't quite support the overlying mass anymore. And in this case, we're going to tear out a whole big chunk of the slope right here. So we're going to move all of this down the slope, and it's going to end up producing an interesting result. So we'll, first of all, chop all that rock off of the cliff line there. And in terms of the final setup, it's going to be pretty interesting because the 3 big sandstone beds there are going to end up kind of laid backwards on the slope here. And we'll put one more kind of tilted backwards behind that. Now, these might have broken up a little bit in the process of moving down the slope. That typically is the case because of those cross-cutting joints that break the rock up into this kind of like 3-dimensional checkerboard. But ultimately, the result is going to be some really huge fragments of sandstone moving down slope, not moving as far as they might have moved if they were part of one of those boulder fall events, but they're still going to be a pretty cool place to hang out. In fact, this is going to be kind of like the tourist attraction in the landscape, because there's going to be all sorts of passageways between those huge kind of ribs of sandstone cutting across the landscape there. We'll fill in the slope as it might look after this. So this is going to make a big gap there in the cliff line. We'll still be able to see those layers. And there's probably going to be kind of like almost like a pit or like a low area behind those bars of sandstone there. So this is going to be the place that you're going to want to hike to with your friends and hang out. It's probably going to be cool in there in the summer. It's going to be a very attractive part of the landscape. And in fact, there's a place called the Devil's Den, I think, in the Ozarks, that ultimately is a feature that is sort of like what I've just drawn here. It's where a large block of sandstone is moved down slope atop weaker layers. Now, there isn't quite the same cliff line geometry there, but fundamentally it's the same thing. The big chunks of sandstone you're going to get with a landslide like this, they're going to be a lot bigger than the boulders that travel farther, but they have moved in such a different way. It's really apples and oranges. It's not the same thing as a single fragment of rock that moves on its own and travels many times its own width down the slope. Because that extra shale there kind of supports everything, it's going to be possible to keep bigger fragments in place with the landslide model. But both of those types of slope movement are really awesome, and a gorge landscape like this in the plateau, again, is really defined by how that extreme gorge topography kind of falls apart over time. All right, so we'll hop back to it now. Okay, so that's the main idea of Appalachian Plateau boulder formation. It's all about those hard sandstone layers and the natural joints or fractures that cut across them. When you got that sandstone cliff line, it's already sort of pre-broken. It's ready to fall apart, and geologically speaking, it just needs a little bit of a tipping point for whatever reason, maybe freeze thaw, maybe erosion on the slope below it, just to destabilize things to the point that there's going to be a collapse and failure. And this type of geology covers a huge area in eastern North America. It actually goes as far as like some of the sandstones, even in southern Illinois. Fundamentally, the slopes operate the same way, and they're really good at making gigantic boulders as a result of that. I found one more of these looking around. This is near Barthel, Kentucky. Can't see a whole heck of a lot here from Google Earth as usual. Bring the LiDAR in there. One really huge boulder down here. That one is almost the size of the first one in the video. Not quite there maybe, but it's generally in the same ballpark. And these slopes are the same as everything we've seen in the plateau, and for that reason, you can expect them to produce these gigantic boulders. So an interesting final way to look at this is just to compare the sizes of the biggest ones that you can find from throughout the entire Appalachians. The images here are all at the same scale, right? So you can look at those, and 100 feet in one is 100 feet in another. All of the biggest boulders there are very close to one another in their overall size. It seems that 130-foot range, something like that, is about the biggest that you see. And I would imagine that has something to do with just the strength of the rock. If a piece of rock much bigger than that fell off the cliff and started going down the slope, the forces, the accelerations on it's probably not going to be able to withstand that. That's why the landslide example in the last sketch is a way that you can move bigger masses of rock, but you can't move them as far. So I would say that the fact that anywhere you go in Appalachia, the biggest boulders that you're going to find are going to be roughly the same size, is starting to speak to actually how like the rock behaves, rather than to some particular detail, maybe in terms of like what made the material fall off the cliff in the first place. So interesting thing to play with. Hopefully get some comments here about people that might have even been to some of these features in the woods. But when you have access to LiDAR and you get a chance to work with it all the time, like I do, you're always seeing something really interesting. I mean, it doesn't just stop with boulders and landslides and things like that. You can use it to interpret geologic structure and find old faults and all sorts of stuff. So fascinating tool. And it's been for several years now, something that literally daily I have to work with. Hope you enjoyed this video. Trying to think where we're going to go next. Not sure, but hope you check it out.